Hey guys, hope you're all doing good and welcome to a new video. So this time we are just going to be continuing from where we left off. Now, a couple of corrections. I accidentally told that this is a screw-type supercharger. It's actually what you call as a Roots-Type supercharger. So the idea is that along this taper, the air is going to get compressed as the screws rotate. Because, it's a positive displacement machine. The air is going to be moved, and since the available volume for the air is getting reduced, it's going to get pressurized. On the other hand, on the Roots blower type, you don't have any taper. You can see that here quite clearly. So the idea is the air basically gets sucked in from the top, and what's going to happen is as the lobes rotate, it's just going to get pushed sideways, and that air is going to get stacked towards the bottom, thereby pressurizing it. Alright, so what we're going to do now is we're just going to flag the inlets and outlets. So I'm going to basically select the angle method, select this guy and assign it to a new boundary. And then we're going to be selecting this guy and we're going to be calling this as the outlets. Now, these two parts are going to go back to the casing itself. So I'm just going to click on apply. Alright, now we don't want our outlet to be like too close. In reality, this supercharger unit is going to be sitting on some type of an intercooler, right? Because compressed air is hot, right? And you want to cool this hot air before it enters the engine. And since we actually don't have that geometry, what I'm going to do is I'm going to manually push the outflow boundary a little bit farther away, right? Is this correct? Well, it's not, but it's not a big deal, because say that you are actually working on a realistic supercharger, then you have the outlet at the right portion, so you don't have to make any guesses. So in my case, what I'm going to do is I'm just going to translate selected boundary, and I'm going to select this guy, and we are going to be translating this along the minus y direction. Alright, so let's start by moving this by 5 mm to see if it looks right. 10, 15, 20, 25, 30, 35, 40. Alright, so that's, I think, a good starting point. Again, this portion of the geometry is usually available if you are working for a OEM or if you are consulting for a OEM, right? So this shape is not super realistic. That's not a big deal because the shape does not matter in our case. All right, so I think that looks good. So the next thing that I want to do is, you can see that the origin is kind of out there, right? So what I want to do is I want to center the origin maybe on this particular point. So what I'm going to do is I'm just going to measure location. I'm going to select this particular vertex, click apply, and I'm just going to take this point, right? So this is basically the location of this point with respect to this particular origin, right? So I'm going to transform, but this time I'm going to use something called as the delta method. I'm just going to put the copied coordinates here. Now what I want to do is I want to translate my geometry. This point is basically 0.0737 meters away from the x-axis, right? So if I push this point by this distance in the negative x direction, then I should basically move this towards the left, correct? So if I put a negative sign here, it's going to make sure that the x coordinate of that red point is 0. So if I basically do the same thing for all of them, then essentially what I'm doing is I'm moving this red point to the origin, right? So let's make sure that entire surface is selected, and let's click on apply. There you go. So now you can see that the entire geometry has been shifted. Why did I do that? Well, this actually helps me provide the rotating boundary conditions very easily. Now for this particular lobe, we know that the rotation axis is z-axis and the rotation center is 0, 0, 0. And if I measure this guy, ideally you will see that you just have an offset along the x-axis, right? You can see that along the x-axis there's an offset, that is the lobe to lobe distance, and pretty much the y and z components are like 0, right? This is a very small number. So this helps us in assigning our boundary conditions with ease. So what's next? Well, the next thing is to basically assign the boundary conditions for our lobes and apply the pressure conditions for the inlets and outlets. So where do these data come from? Well, you usually get them from something called as a performance curve. Now typically for a supercharger, when it's rotating at a particular RPM, it basically delivers a given mass flow rate for a given pressure ratio, right? So the idea is that depending upon the RPM and depending upon the mass flow rate and the pressure, you have a particular efficiency for the supercharger, and the idea is to basically have all these details when you're starting to simulate. Now as far as the CFD engineer or the CFD analyst is concerned, The only thing that you need to be worried about is choosing a point that is still inside this performance map. Oftentimes you might be playing with a supercharger case setup and you might be using a boundary condition, you might be using an operating point that is completely not realistic. In those cases you will definitely get wrong results. So from a CFD analyst point of view, you need to make sure that you get your hands on this performance data so that you can definitely be sure that you are setting up the simulation for the right conditions. So in our case, what we are going to do is we are going to go for a pressure ratio of 2.0, which means the outlet to inlet pressure is going to be 2.0. which means the ratio of the outlet to the inlet pressure is going to be 2.0. So at the inlet, if the pressure is 1 bar, the pressure is going to be 2 bar at the outlet. And in our case, we are going to say that the rotor is basically rotating at 36,000 RPM, right? So 36,000 RPM is nothing but 36,000 divided by 60 RPS, rotations per second, right? Since 1 minute is 60 seconds, you're dividing this by 60. And then what you're doing is you're converting this rotations per second into degrees per second. Now one rotation is 360 degrees. So you take your original RPM, you multiply that by 360 and divide that by 60, right? Now 360 by 60 is equal to 6. So the only thing that you're left with is 36,000 times 6, which is 216,000. So this is going to be the speed at which the lobes are rotating. Alright, so the next thing that you need to understand is the direction of rotation, right? So we definitely know that the lobes should be rotating in opposite directions, correct? But you still have two ways to do that. So the idea is once the air comes in, we want to push it towards the outer wall and then we basically bring it towards the outlet from the downside, right? So in other words, if I hide this guy, this orange rotor should be rotating in clockwise and the yellow rotor should be rotating in anti-clockwise direction. Alright, so that's basically it. So let's go ahead and set up the case. So I'm going to start with begin case setup. I'm going to click on general flow, click on apply and done. And then in this case, I'm just going to have air as my material. Alright, and then what I'm going to do is I'm going to click on run parameters. We are going to be doing a transient simulation because the lobes are rotating. So let's click OK. And as far as the simulation parameters, like we want to make sure that we run this for at least a few rotations. So how do we go about that? Well, this is basically rotations per second, right? So if you take this RPS, this is basically saying that you have 600 rotations per second, correct? I think I did the math right. So 600 into 60, that's going to be 36,000. Now, how do we calculate the time per one rotation? Well, if you have 600 rotations in 1 second, then the time taken for one rotation is going to be 1 divided by 600, right? So that is basically seconds per rotation, right? So for one rotation, if it takes this much time, then for 5 rotations, or let's say 6 rotations, then we are going to be taking 6 divided by 600, correct? This is for 6 rotations, right? So that's 1 divided by 100, which is 0.01, right? So whenever you calculate run parameters, make sure that you apply some kind of logic. So 0.01, I believe that is correct. All right, and I'm going to say that the start time is 0. We want the initial times to be 1e minus 9, and we want the minimum times to be again 1e minus 9. Maximum time step can go up to 1 second, but it never does in these type of simulations. And since Converge is going to be using a dynamic time step algorithm, it's automatically going to march towards the highest possible time step. So let's click on validate and click OK. As far as the solver parameters, we typically don't touch this unless we have some type of convergence issues. So now we are ready to assign the boundary conditions. But before we do that, I think it might be an idea to just clean up some of the unused boundaries. So I'm going to select this guy and I'm going to delete these unused boundaries. And you can see that there are 2 triangles in boundary ID 0, so that needs to be fixed. But before I do that, I'm just going to name the parts. So let's see here. So this is going to be left lobe, and obviously this is going to be the right lobe. Oops. And what else is there? Well, so this is your casing, so I'm just going to call it as casing, and this one right here is the inlet, and this one right here is the outlet. Alright, so let's figure out where these two guys are. So I'm just going to enable these two boundaries, and let us see. Okay, that seems like a very small triangle, and I think it has to be with the casing, right? So there are a couple of ways to do this. One thing is to just go to isolated triangles, just make sure that the group size is 2, and then click on fix isolated triangles. When you do that, the number of triangles in the not assigned boundary automatically becomes to 0. So this is perfect. So let's get started. At the inlet, what I'm going to do is I'm going to say that we are providing an inflow boundary condition, and the pressure there is 101325, or in fact I can just give this as 1 bar, right? Ideally I would need some kind of measurement data here, so in this case I'm just going to go with 1 bar, but since we don't have that, I'm just going to go with 1 bar here, and we are going to be using a temperature of 300 Kelvin, and air is our fluid. And at the outlet, what I'm going to do is I'm going to say that we have the outflow boundary condition. I'm going to say that the static pressure there is 2 bar. So again, I cannot insist on the importance of getting these boundary conditions correctly, and they need to be consistent with the RPM that you have selected. Now in this case, there will not be a backflow, but if there is, we just have to make sure that air is going to be the fluid that returns at 300 Kelvin. And if you take the casing, we are just going to apply the wall boundary condition. Alright, so let's just hide the casing here so that we can look at everything. So for the right lobe, what we are going to do is we are going to say that it's a wall, and it is a rotating wall. The rotation rate in degrees per second, right? So this is degrees per second. So I'm just going to copy that, and I'm going to paste it here. And then for the rotation center, I'm just going to copy this guy, and I'm just going to paste it here. So that's going to be my rotation center. And the rotation axis, so this is where you need to be careful, right? So we want this to be rotating in clockwise direction, right? The orange lobe, we want that to be rotating in clockwise direction. So if you rotate it about the z-axis, Converge is going to use the right hand thumb rule, which means the lobe will actually rotate in anti-clockwise direction. You don't want that. So what you can do is you can just put a negative sign here. Alternatively, you can put a negative sign in the RPM as well, but I typically like to do that in the axis. Alright, so that looks good. And for the left lobe, the conditions are much more easier. It's a wall, it's a rotating type wall. Now the rotation rate is 216000. I believe that's right, so let me just check. Yep. The rotation center is going to be 000, and the rotation axis for that can be the positive z-axis, right? Because the yellow colored lobe should be rotating in the counterclockwise direction, which is about the z-axis. So that is perfect. So we're going to click on validate, and that's basically it. Alright, so let's go back to the case setup, and we're going to add a region. So in this case, we just need one region. I'm going to add air as the working fluid. Validate and click OK. Now we go back to boundary, and what I'm going to do is I'm just going to say that everything belongs to region 0. Alright, so then for turbulence modeling, what we are going to do is we are going to start with RNGK epsilon. Click on validate and click OK. And as far as the base grid is concerned, we are initially interested in just getting a coarse simulation because we want to make sure that the setup runs perfectly. So let's redisplay everything. What I'm going to do is I'm just going to measure the cell count for a given base grid. So we'll start with 4 mm. It basically says that the total cell count is about 33,000. Now this assumes that you have a perfect cuboidal shaped geometry, right? This is just an estimation. So in our case, what we can do is we can, I think, go to maybe a 2 mm base grid to see what happens. And as far as the output files are concerned, we need to make sure that we are getting, so it's 1e minus 2 seconds, which means in order to get 100 output files, this needs to be 1e minus 4. And what I'm going to do is I'm going to basically writing a restart file every 5e minus 4 seconds, right? So this way, in case the simulation crashes, we might be able to restart it from that crash point itself. And let's click on validate, and let's click on OK. Oops, let's go back to the output files, and for text output files, I'm just going to put in a value of 1e minus 9. So this way we can track our mass flow rates very well. So let's click on validate and OK. Post variable selection, nothing fancy is required at this point. global transport parameters, nothing to be done there as well. So with that, our setup is complete. So the first thing that I want to do is I want to make sure that I run a no hydrodynamic solver, so that if there are any issues with the mesh motion, we can actually capture it. Let me check the normal direction, and clearly the normals are all incorrect. So I'm going to transform the normals, and I'm going to click on attempt to fix all normals and click apply. There you go. So that has fixed it, right? And we're ready to export all our input files. And I'm just going to go back to my supercharger setup folder. I'm going to create a folder called base setup, and inside that we are going to select folder, we're going to click on OK, we are going to export everything, and then let's open up Converge, and we're going to go to supercharger setup, we're going to go to the base setup folder, and I'm just going to run Converge to see if it actually runs through. So here you can actually see that the time steps are starting to grow, and you are having about 200,000 cells, which is actually much more than I anticipated, but that's fine. So what I'm going to do is I'm just going to let this run, and if it crashes, that means that as the lobes are rotating, they're intersecting somewhere. If it is not crashing, we know that our boundary conditions have been set up correctly, and then we can move on to the next step. So I'm going to pause the video right now, and I'll continue.